All right, good evening, everybody. Thank you for coming out to Cafe Sci this evening. If you give yourselves a nice round of applause for being out here, I think that definitely deserves applause. We definitely applaud your dedication to learning, and we hope that we can continue to provide wonderful opportunities like we have here at Cafe Sci for your enrichment. So we can't do Cafe Sci without the generosity of sponsors like PPG, who's our chief sponsor for Cafe Sci, and through contributions from our members and guests at Cafe Sci. Any donations to this program do go a very long way. So if you are in a position to make a monetary gift, that's much appreciated. If you cannot make a monetary gift, the best thing you can do is come back next time and bring a friend with you. Bring a family member, or even bring an enemy. Anyone you bring here to Cafe Sci is going to help us keep this program running. And speaking of the next Cafe Sci, we will be off in April. There is the NFL draft happening right next door, and you might not want to be around here during that time. The traffic will be a nightmare. So we'll be coming back in May, and you'll be able to find all of the details for the next speaker on our website shortly. I'd also like to thank the Pittsburgh Quantum Institute this evening for collaborating with us here at the Science Center for tonight's presentation. Dr. Monroe, who we'll introduce in just a moment, is also presenting a talk at the PQI 2026 conference this week to STEM students, and there's a lot of really great quantum science being discussed here. You can find more information about PQI 2026 and the Pittsburgh Quantum Institute at pqi.org. And without further delay, I am pleased and honored to introduce tonight's speaker to all of you. Tonight we are joined by Christopher Monroe. Dr. Monroe is the Gilhuly Professor of Electrical and Computer Engineering and Physics at Duke University. He's also the co-founder and chief scientist of IonQ Incorporated, the first public quantum computing company. Dr. Monroe has pioneered nearly all aspects of atom-based quantum computers and simulators. He's a key architect of the U.S. National Quantum Initiative and is a member of the National Academy of Sciences. He's born and raised in Detroit, so being in a nice Rust Belt city like Pittsburgh is a great thing to have someone who really understands our region. So if you wouldn't mind putting your hands together and welcoming Christopher Monroe to the stage.
Thanks for the wonderful intro, and it is indeed a great pleasure to be here. Although you mentioned the NFL draft next door, that's one thing, one aspect, our two cities that really diverge, and that is having a good football team. Anyway, don't know what that's really like. Okay, so this is meant to be hopefully an interchange. The subject is it's a tricky subject. Even among scientists who practice in the field, there's so many different interpretations. You've all heard of some of the weird aspects of quantum physics, and I can't think of a better word than weird to sort of describe it. And we're taught, if you get a physics degree, you're taught the fundamental aspects of quantum, and it's very difficult because there are really no analogies of what this theory is in real life. And that's unlike most other fields, like in civil engineering, designing a bridge. We can really picture that. We understand how big objects move, how they interact with each other. And quantum is not so. Now, so you've probably read about quantum computing. This is a topic that's very hot now. It's been on a steady rise for the last few decades. And the big companies, the big computer behemoths, have very large programs in building these so-called quantum computers. And the title, if you read the title of this talk, I mentioned quantum computers for cocktail parties. So your next cocktail party, I hope you're at least able to define things and perhaps get a feeling for how strange it really is. It does make good cocktail party banter. And I'm afraid, I don't see any of these CEOs in the room. I'm afraid most of the CEOs at these big companies, it's amazing to say this, but I don't really think they know what they're doing. Now, however, what they're doing at a high level is very good. It's a real field, and I'll tell you a little bit about what it is and what it can be and what it can do. These are real machines, and these big companies, to their credit, have sort of invested wholly into these fields. They believe it is a future for some of their technology, even if they're not really, I'm not convinced they're building the right way, but that's okay. It's still an academic subject, so universities like Pittsburgh and CMU in particular, the Pittsburgh Quantum Institute, has wonderful research in that field. The big companies, the small companies, the government labs, so it's infiltrating all over. And so I'm going to spend most of my time here, very pedagogical, defining terms, what it is, what the opportunities are. And I want you to yell at me and don't throw anything, but you can ask questions anytime. I really want this to be a dialogue. It's a fun topic. Okay, so this is a little bit of a hyped graph, I might say. This is human progress over time, and we all recognize in the last few centuries eras like the industrial age, of course, the steel mills here in Pittsburgh and the auto factories in Detroit played a big role in that. But we've seen over the last 60 or 70 years what we might call the information era, computers, the building up of silicon so that we can wear very powerful, I don't have an this is all mechanical, but we can wear very powerful computers even on our wrists these days. And that has, of course, revolutionized society. Now, many believe that in some way, that will eventually displace these machines, or at least append these machines with a new type of machine that has new powers, the so-called quantum age. Now, the reason this is actually not hyped is I didn't label the time axis. I mean, we all know that this was maybe 100 years ago or 200 years ago, and this is sort of right now. We're somewhere on this blue curve. We don't exactly know where this quantum age will take over, but I will prevent compelling arguments that it will. It will add to our ability to compute things. So I want to really dive into that. Okay, can't be any questions on this. This is all fluff so far. You might argue that in the 20th century, one of the advents was information theory, the idea of storing information, processing information, the computer era. These two men really are arguably responsible for that, Claude Shannon and Alan Turing. You may have heard of Alan Turing and his so-called Turing machine, which is an abstract model of any computer, any non-quantum computer, any regular computer, how it works. It has a tape, it has a head that can respond to what's going on each bit of the tape, and the tape moves across. You can add numbers using this type of an idea, multiply. All computing can kind of come down to this. Now, the important thing is that this device is not a transistor, it's not silicon, it's not magnetic, it's not optical disks, it's not the internet. It doesn't matter. It doesn't matter what the physical platform of the computer is. This is a model of how you compute. Now, Shannon, he was at Bell Labs. Turing was in Britain, famously during World War II, building computers to break the Enigma machine, the German coding machine, so it's cryptography. And Claude Shannon here at Bell Labs spent most of his career, invented the idea of a bit and how you measure information. So we're pretty familiar with bits, zeros and ones. It's an alphabet. It only has two letters, 0 and 1. And so it makes sense that you should be able to encompass information in a sequence of bits, right? Now, in the English language, we have 26 symbols. Now, 2 to the power 5 is more than 26. 2 to the power 4 is less. So each English symbol carries between 4 and 5 bits of information. It makes a lot of sense. So we can, of course, encode any character in English, a book. Each 5-bit string is a single letter, and so forth. And the important thing is that Shannon, like Turing, he abstracted the notion of information. It's kind of funny to define information in terms of a mathematical formula. I won't go into that formula there. But this was very important, these two men and their abstractions, because it paved the way for us to build devices. We didn't have to build a particular device. We could build any device as long as it could store bits and process bits. And so this, not coincidentally, gave rise to the era of digital computers, and you've probably heard of these. You've probably heard of ENIAC. It was actually at the University of Pennsylvania. It was an Army project. The first digital computers built out of vacuum tubes. This is Turing's version. The Brits beat us on this one, actually. That's the Colossus machine. And the Soviets, actually, I have to put this up because my wife is Russian, and she likes me to put it anyway. But the Mesm machine, apparently, the Soviets built around the same time, and I'm sure they stole everything, all the plans for it to get it. But these are made out of vacuum tubes. Each little individual transistor or switch element is one of these vacuum tubes, very similar to the ones you'll see in an old amplifier, an audio amplifier. Now, they were not very reliable. They would break. I mean, these are glass things with a vacuum in the middle, so if you bump them, they wouldn't behave. Very sensitive instruments inside those vacuum tubes. So it was very difficult to imagine scaling these computers to more than a few thousand vacuum tubes. And so it could only do very simple arithmetic. Now, along came, because it doesn't matter what your computer's made of, as long as it has a switch, as long as you can represent bits and have appropriate interactions, you can build a computer out of anything. And this actually looks a lot worse than this. I mean, at least this was clearly manufactured by a company, and this is a physics experiment. This is the first solid-state transistor, also at Bell Labs in the late 40s. And what you see here is a semiconductor. This dark piece is a chunk of germanium, which is a semiconductor, not exactly an insulator, not exactly a conductor. And it has two leads on it, and a current will flow through that germanium depending on the current that's coming through this gold foil down here. And all of the action, the entirety of it, is in this little junction down there. And the humidity had to be just right, and it had to be low vibrations. So this is a physics experiment, but the important point is there's no vacuum. And you could imagine making that much more reliable, making it a lot smaller, and scaling things up. And while we didn't do it out of germanium, we used a different semiconductor called silicon, and of course that's the silicon era that really underlied the growth in computing. You've all heard of Moore's law? Moore's law is it's an empirical law, meaning that there's not a theorem or anything, but it turns out by dumping more and more investment into miniaturizing and regularizing silicon, we were able to pack more and more transistors on a chip. So this plot, over time, over the last many decades, it started a little earlier than this, but this is a log plot, meaning every division is a factor of 10 more. So a line that grows on this plot is actually exponential growth. You increase by a factor of 10 every decade or something like that. And this is the number of transistors on a chip relative to 1978, which is 1 by definition. So you can see over a few decades, we got 100,000 times the packing density of transistors. And that largely linear slope, the exponential law, it's called Moore's law, and you'll notice that it's actually sort of turning over a little bit. We're not enjoying such growth as we had before. And that's actually for the very simple reason that the current transistors on our computer chips, they're so small that if you miniaturize them even more, they're almost the size of a single molecule, maybe a large molecule, maybe a protein or something like that. But it's hard to squeeze more room when you're down to the limit of a single molecule. So this plot does tell you that Moore's law is not going to continue forever. It's going to end. And so this is a little bit of a motivation behind quantum computing. What's next? Is there another way to keep growing? And what's amazing to me is that many, many years ago, in 1959, like 70 years ago, Richard Feynman, a very colorful American physicist, who really was one of the fathers of quantum electrodynamics, so a theoretical physicist, really. He liked to tinker, and he was very interested in things like Moore's law. And he imagined in one of his lectures, actually, he imagined what would happen if you shrunk down to individual atoms for the transistors. And he said, well, what would happen is that we would have completely new opportunities for design. And the reason is a little subtle. The reason is, at the level of individual atoms, the laws of physics are different. And whenever you have new laws of physics coming in, that means there are new opportunities. And back in '59, he nor anybody else knew what those opportunities would be. And those opportunities are now pretty clear. It's a new way to compute, quantum computing. And so now finally, I'm going to, this is the cocktail part, the cocktail party part. I'm going to define the pretty much quantum physics, almost pretty much all of it. And I'm going to try to do it in under 5 minutes. And there's very little mathematics, because that's not going to help you understand what it is. It'll help you model the actual behavior of an electron around an atom or something like that, or the behavior of electrons that go through a conductor at the quantum level. That's fine. You need math for that. But the rules are actually very simple. And they're weird, but that's okay. You don't need an advanced degree to appreciate weirdness, okay? Okay, so here we go. Any questions? I want to stop. That was sort of intro, hopefully to wet your whistle that quantum physics is really important. It's not just a theory. It's going to underlie new technology. Yes?
Just had a quick question. Was Feynman the first person who used the term quantum mechanics?
No, this was quantum. In fact, it was largely codified about 100 years ago in 1925. And the players there were, well, Albert Einstein, you've heard of these names, Erwin Schrödinger, Werner Heisenberg, Niels Bohr, there's several of them. And it's interesting that it did take about 20 years for it to be accepted because it's so weird. And in 1925 is really when the Schrödinger equation came out. I'm going to show you what that is. And Heisenberg sort of codified the laws of quantum that we use today. So it's about 100 years ago. Okay. So any other questions on background? Okay. So the next 5 minutes, you're going to learn exactly what quantum physics is. And then we're going to move on to what a quantum computer is and where things stand. Okay, so quantum physics has only 2 rules. It's only 2. And for a physicist, for a theoretical physicist, that's one too many. You know, in physics, we like to think of ourselves as the king of science. Everything comes from one law. It's a beautiful law. And I just sounded like President Trump there, didn't I? Sorry. But it is. Having one law at the very top, everything comes down from it, even if not in practice, but at least we feel comfortable that we understand everything below because there's only one law. Actually, quantum is weird. There are 2 laws, and you can't get one from the other. So that you might think, well, where is that? There must be one law above both of those. Don't waste your time. It's been over a century, and many careers have been lost wasting their time down that rabbit hole. Almost all of physicists accept these 2 laws. They work. They've been tested to better accuracy than any other law in all of nature by far. And that doesn't mean they're right. It just means that if there is an overriding law, it's going to probably be as weird. Okay, so here we go. The golden rules of quantum mechanics. There's only 2 of them. That's the good one. Good news. Okay, rule number 1, you may have heard that quantum physics is actually a wave theory, the Schrödinger wave equation. Well, quantum mechanics, rule number 1 is that everything is a wave. That's not very useful to say that, but we describe things by their wave-like properties. And waves, I mean, we're very familiar with waves, water waves on the surface of a pond, sound waves, a little more subtle electromagnetic waves, because they're a little more abstract. But sound waves are good, or water waves are even better because you can literally see them. And water waves on the surface of a pond have an equation that describes how they're going to move. But how many of you know that equation? I mean, who cares? We see the waves, and we see how they propagate. Now, one property of waves is that waves can be in states of superposition, which means they can have multiple, waves can have multiple states at the same time. I mean, in music, we can hear many tones at the same time. A single tone is a sinusoidal wave of a certain frequency. We can experience many tones at the same time. Our eardrum vibrates at many frequencies at the same time because the wave that approaches the eardrum is in superposition. There's nothing radical about that at all. So superposition. Where is a wave? If I throw a rock on a pond, the wave's everywhere. It's in a superposition of position where it exists. Okay? So that's fine. Now, when we apply quantum mechanics to a bit, a 0 or 1, we have something called a qubit or a quantum bit. Very little jargon in this talk, but I want to throw this at you because whenever you see that notation with a line, something, and then a bracket, that means it's a quantum state. It's a quantum thing. And in this equation, the quantum state is a superposition of 0 and 1. And that means this is not the number 0. It's not the number 1. And this is not addition in the normal sense. This just means we have a superposed state of 0 and 1. A and B are just coefficients. They're weights. It tells you how much 0, how much 1. Here's a drawing, a poor drawing of an atom with 1 electron in blue. You'll notice the electron is in 2 places. That's okay. The electron's a wave. It's distributed in 2 different energy levels, say. And it's hard to draw, but we can think of storing information in a bit, but it's a quantum bit, so-called a qubit, okay? And this turns out the numbers A and B, they do follow a wave equation. I said there would be no math. I'm just showing you, yeah, they have a wave equation. I'm not going to talk about that wave equation. You know, water waves have a wave equation as well, but we don't need that equation to accompany this beautiful painting. We know what's going to happen with this wave. We appreciate at the beach when water gets shallow, the waves get higher and slower, and they fall over each other. There is math behind it, but who cares? It really doesn't add to the beauty and to the depth of what we have here. So that's rule number 1. We have superpositions. Really, nothing new here in a way. Okay? Yeah. There's a question?
I didn't follow you on superposition. You just defined superposition.
Okay. I'll use a prop this time. If this water bottle is, I'm not going to choose my words carefully, but this water bottle can, let's say it can be in 2 places, that place or that place. But we know water bottles and objects that we experience to have definite existence. They have definite positions in reality. The baseball's here. It might be moving fast, but at any point in time, it has a definite position. Now, I'm claiming this water ball is actually a wave, and the wave can have 2 pumps. So that's a superposition. So what I'm saying, it sounds ridiculous, but if we believe that this bottle is a wave, then yeah, there's nothing wrong with this bottle being in 8 places at the same time, but the simplest version is 2. Well, the simplest would be 1, but then it's trivial. There's no information there. You need a bit. You need two levels. So what I'm calling a superposition is that this bottle is in 2 places at the same time. I think your question is about rule number 2, I'm guessing. But we haven't gotten there yet. So your question is, what does a superposition mean? What does it mean? Okay, so here's the answer. We have to invent another rule because we never see bottles in 2 places. We never see anything smeared out in multiple places. So we have to invent a second rule, and this drives people crazy. The second rule means rule number 1 is fine, you just can't look. That's basically, this is the truth. This is how we teach quantum mechanics. There's 2 parts. There's the wavy part, and then there's the part where you look. Because the part where you look, you can't use rule number 1. And if you look, fortunately, when you look, you only get definite states, but they're random. And that's the importance of these weights. If I had a 50-50 weight, A and B, then I would have to use probabilities to decide that there's a 50, it's like tossing a fair coin, whether this bottle's over here or over there. That's rule number 2. And you got right to the point there because rule number 1 just doesn't cut it, right? What use is it if we can't look? And rule number 2 is very, very strange. This is, to me, this is the weird part, not this. It's this. Why is it weird? Well, for many reasons it's weird. It seems, well, here's one reason. It seems that by merely looking at something, you affect that something. Sometimes the technical term we use is sometimes we call it wave function collapse. This wave that had 2 humps now it only has 1 hump, and you don't know which one until you see it, and then you only have 1 hump, and then you're happy. But looking at something, you can go really far away and not directly interact with it, but just by gaining information, you've changed that system. That's weird. To me, one of the weirdest things is that, so this is a little technical as well, but the probabilities are given by, they're not exactly A and B, but they're given by A and B. Don't worry about the math here. To me, what's strange is probabilities. We all are comfortable and we all understand probabilities, or well, we use probabilities. It's almost philosophical, the use of probabilities. We use them when we flip coins. A fair coin has a 50-50 chance. We use probabilities to discuss the weather. 50% chance of rain. Now, we use probabilities in society when we are ignorant of something. It's a way to it's a way to accept ignorance. When I flip a coin, I don't know exactly how hard I flipped it, or how how much I rotated it, how strong gravity happens to be in this place. So instead of knowing all those details, we're ignorant, and we're okay being ignorant, and we'll just use probabilities. Same with the weather. Of course, we have no great models of atmospheric chemistry at a level where we can predict with certainty whether it's going to rain or not. But in quantum, there's no ignorance here. It's not about ignorance. You have to use probabilities. They come along for the ride. When you measure something in quantum, it's inherently noisy. It's inherently probabilistic. That's weird. And Albert Einstein never accepted this. He never accepted quantum. He thought there was a rule at the very top. We just didn't know it, or we just don't know it. And he has these wonderful quotations. One of them is, God does not play dice. Who is rolling the dice? Who is deciding? It's a really good question. It's philosophical, and it's where there's arguments and so forth. But that's it. That's quantum. That really is all of quantum physics. So you can take that to your next cocktail party. There's no more understanding of the concepts than what you already have now. Now, there's this, and this math can get really complicated. That's true. But it won't add to the concepts. All right.
I got a question for you.
Yeah.
Up on the screen, it shows an eyeball looking at these two states, and the eyeball makes one of the states solidify, or whatever you want. Okay. What if there are two eyeballs looking at the exact same thing? Are they going to see a bottle of water over here, and the other eye is going to see a bottle of water over here?
Oh, that's good. Okay, you're trying to drag me down the hole of defining consciousness. Let's try to not. And it's my fault. I put the eyeball there. Let's go back to the water bottle. So we have a water bottle here and here. Now remember, if it's in both places, then nobody's looking. But that also means that the air in the room can't be here, because the air knows. I mean, look, if the bottle is here, there is no air here. There is air over here. But if the bottle's over here, the air evacuates here and moves over there. So somehow, without a consciousness, the air adapts to the situation. So if it's in both places, what does the air do? We weren't talking about the air, but now it's sort of part of the system. All right, let's get rid of the air. We need perfect isolation. This sort of hints at the rest of the talk. Making quantum technology means we have to isolate things severely. So let's pump out all the air, big vacuum pumps. There's no air. Well, you can't do it perfectly. But let's say we pump it out down to one air molecule that's running around this room. And this bottle is in two places. Now, the air molecule eventually is going to want to hit the bottle. And the air, if the bottle's here, it'll say bounce off the bottle and hit that wall. If the bottle's over here, that same air molecule will hit the back wall instead of the side wall. So what does the air do? Well, we made troubles to put this bottle in two places. Let's just say the air takes two paths at that point. The air goes that way, and the air goes that way. That's okay, I guess. One air molecule is not much in addition to this. But now the wall in the back vibrates a tiny bit from that air molecule. Or was it the side wall? Oh, well, let's just have the walls be part of the system. So bottle's here, and that wall vibrates. But now the building shakes a certain way. The Earth gets involved. So pretty soon you have the entire universe involved in this superposition. In practice, what we do is we form an invisible box and assume it's perfectly isolated. So the answer to your question, if you have two people observing, I would answer it by saying whoever observed it first, that determines where it is, and the other one sees the same. You might say, what if they're exactly tied?
That's why
Yeah.
in the real world, two people look at you and they only see one view. Using that a lot.
Yeah, but
Look at you right there and you right there.
the air would have long before you're able to see. the air, and you have to breathe, so there's air around us. Yeah, so these, you can see how these questions, I mean, it's a good question.
But I mean, the important answer I think you came up with was that the person, the eye that sees that observes first, sets the reality.
Whatever interaction happens first. It could be a single air molecule, it could be eyeballs, it could be whatever. It could be a light ray somewhere that bounces off. Whatever gets in there first, then all the dominoes fall. Yeah, good questions. Anybody else? Okay. Now, it turns out there is, to my mind, there are some analogies of superposition and measurement. One that's particularly good involves an optical illusion. And I use this one because it scales to many qubits. That's what we're going to get in a minute. A qubit is in a 50-50 superposition of 0 and 1. Again, I'm representing it by a cube that is drawn with ambiguous perspective. You know, when you draw real perspectives, the lines are supposed to converge to some horizon. I didn't do that here. They're perfectly parallel. So the front face of this cube, it could be pointing down and to the left, or the front face could be pointing up and to the right. And when you look at this cube, you might see that it flips. It's sort of both. They're sort of both there. Okay? And when you lock onto one perspective, you often stay there. That's like the wave function collapse. That's like a measurement. That's rule 2. Rule 1, it's flipping, and rule 2, you observe it. It's a kind of a weak analogy, but I like it because, and here are the two definite perspectives. I like it because it scales. Now, this is a funny quantum state of exactly 2 qubits. Now, 2 qubits, 2 bits, there can be 4 possibilities of 2 bits, right? 0, 0, 0, 1, 1, 0, and 1, 1. Now, I've excluded the odd ones, 0, 1, and 1, 0. I prepared somehow a quantum state to be a superposition of heads, heads, and tails, tails. 0, 0, and 1, 1. Those are the only 2 part of the superposition. Now, when you look at these cubes, it's a decent analogy to that funny state. Because these cubes, this is the illusion part, the cubes will almost always lock into the same perspective. They're correlated. They're random individually, but they're perfectly correlated when considered together, right? Now, it's not a perfect analogy, and if you work hard, you can see both. You can see the 0, 1 and the 1, 0. But if you close your eyes and shake your head and do it again, you'll naturally pop into one of these. Now, this type of superposition has its own buzzword. It's called entangled. You may have heard that term. An entangled quantum superposition is one that has an inherent linkage. And what's neat about quantum entanglement is that, now, forget the cubes now. Look at this quantum state. These are the 2 possibilities, 0, 0, and 1, 1. Now, I never said that these qubits are together. Maybe they were together at some point, but let's separate them in space. In fact, let's leave one on the Earth, and you can take one to the moon. But we've isolated them perfectly, and they've not been observed by either of us. As soon as I measure mine on the Earth, whatever I get, I know immediately what you have, right? If I measure 0, that means the wave function collapsed to this, and I know you have 0, even without calling you, or even without you telling me. If I measure a 1, I know you have a 1. Faster than light could make the passage from the Earth to the moon. I know immediately. So this is very interesting. Another Einstein quote is that this is spooky action at a distance. He thought this was sort of the smoking gun on why quantum was ridiculous. You can't have spooky act. Nothing goes faster than light. He had proved that. That was well accepted in 1925, his theory of relativity. This entanglement is very strange. It allows you to have these correlations, almost having wires without wires. Yeah?
How does the entanglement happen to begin with? How are these 2 lights where they are?
Yeah.
How are they entangled to begin with?
Yeah, good question. almost certainly they were prepared together somehow. There had to be some kind of an interaction. I mean, there are many ways to do this, but they will be in close contact. Atoms do this all the time, yeah, at some point. But then you have to, that's the hard part. It's very hard to separate them.
And the one, a previous gentleman actually said, I assume that you agree with him, is that you could take, if two are entangled, then one could be on Earth and one could be an Alpha Centauri.
Yeah.
And you affect one, and that one does the same thing, right? Or whatever.
You have to be, when you said you do one thing here, that one does the same thing. Okay, so here's the problem with that statement, and that is, all I said is that when you measure one here, I know exactly what your value is. That's not the same thing as communication. And the reason is, this goes to Shannon actually, if I want to communicate, you're an Alpha Centauri and you want to send help, get me out of here. You have to send information to me. You have to encode bits in a certain way. Now, if we have all this hidden wiring, if we have a bunch of pairs of let's say we have 1 million atoms. We label them 1 through 1 million, and you have 1 million, and they're all entangled pairwise. So when I measure the first one, I see a 0. Oh, he must have a 0. I measure a 0, you have a 0. You have a 1, 2, or sorry, 0, 0, 1. All I get is a random bit stream, and I know you have the same random bit stream. I don't know you're in trouble.
You don't know what?
I don't know that you're in trouble. You're not able to, because random numbers carry no information. There is no information transfer. And that's actually the resolution of this so-called paradox that Einstein came up with in 1935, actually, before Shannon's papers on information theory. And that's the resolution. But you were right. You were right there. It's
And I think I probably misread a previous, it's spooky action, not spooky attraction.
Well, this is Einstein's word, but the question is, what is that? Is there really action happening? I would say that's the wrong word. And you keyed on the problem with that quote of Einstein's. It's not action, because I can't tell. I mean, all I know is that we have the same random number. That doesn't mean I cause an action at your end. So it's very subtle. You can see how these things, okay? So there's no information transfer using entanglement like this, faster than light. But there's still something there. I mean, I don't get information, but we have correlations, even though they're random. Yeah, so, all right, the rules were, I mean, the rules, there they are, but yeah, you can get into some conundrums like this, just looking at those rules. Okay, so there are the definite states. Okay, finally, we're going to get into quantum computing. What is it? Well, this is a hint. Quantum computers involve lots and lots of qubits. We're going to imagine a bunch of qubits. And we're going to compute on them. Of course, we're going to compute on them just like we do with regular bits. We can compute the square root of numbers, or we can the logarithm, whatever you want to do. We're going to compute using qubits instead. And so the way I think of quantum computers is it's sort of a good news, bad news, good news. I mean, the good news is that these qubits seem to carry, you know, they can be in superposition, so we should be able to do massively parallel computing. So here's the good news, bad news, good news. And again, another equation, sorry, but you understand this equation by now. This is 3 qubits. And with 3 qubits, there are 8 possibilities. So we have 8 weightings. That's these numbers, a sub 0 all the way up to a sub 7. Those are the probabilities. They give you the probabilities. And this is just 3 qubits. And the grayscale of these 8 dots is sort of like the weighting. Let's say dark means that you have a high weighting, and white means you have a low weighting. Might be backwards. Doesn't really matter. Now, what's cool about having these 8 numbers at the same time is that we can make one computation on the system. We can evolve this quantum state using the wave equation. There's math and all that. But you can imagine we can compute 8 things with one turn of the crank. That's parallel processing. Now, 8 is not a very big number. It doesn't take my laptop long to compute 8 things. But that's the magic of exponential growth. Every time you add a qubit, you double the possibilities. With 4 qubits, there are 16 states. With 5, there are 32, on and on and on. By the time you get to 300, it wouldn't seem huge, but 2 to the power 300, that number is huge. We can't deal with numbers that big. We can't deal with anything that has 2 to the 300 parallel inputs, because that's more than the number of atoms in the entire universe. The universe isn't big enough. So this is the huge good news. It's like compound interest, it's 100%. You know, every time you add a quantum bit, you double your money, you double the storage space. And you get to compute all these exponentially many outputs, all with one turn of the crank. That's the good news, and you know what the bad news is, because this is rule number 1. This is the wave function and so forth. But we have to, it's a computer, we have to look at it. And when you look at it, it's really bad. You only get one answer, and you don't know which one. You have no idea which one. It could be 1 out of 2 to the 300 possibilities. By the way, 2 to the 300 is about 10 to the 90th. So 1 with 90 zeros. And you get one of those answers at random. What use is that? It's totally useless for most types of problems. So the only way to know what you got was to invert this function and then look at what input it corresponded to. But why not just do it serially on your laptop, compute one after the other? So clearly, this is not all there is. And this is, this takes us into the 1990s, when it was learned that, or it was first pointed out, that before you make a measurement, we're going to use rule number 1. We're going to keep using rule number 1. And remember, waves, not only can they be in superposition, they can interfere with each other. Like water waves do this, right? If you have two like boats that go next to each other, the waves sort of collide, and sometimes they double, and sometimes there's nothing. They interfere. Sound interferes. You've heard kind of beating when two instruments play notes really close to each other. You hear a beat note, a warbling. That's interference. Well, quantum waves also interfere, and the idea of a quantum computer, and this will sound kind of useless and abstract, these red dots are called quantum gates. They steer the wave function. This is rule number 1. We're applying gates that allow interferences to happen. And in some magical cases, you can prescribe a pattern of gates so that almost everything interferes to 0, and you're left with only one answer. Before you measure, you're left with only one answer, or a few. But not 2 to the 300 answers. That would be useless. But if you end up with a few, you can repeat this experiment many times, and you can get an idea what those answers are in their completeness. And when you measure that one output, it can depend on all of those inputs. Now, the magic is well, how do we know we don't need 2 to the 300 gates to do that? Because if that's the case, then we're out of luck. There's no time to run 2 to the 300 gates. But there are some problems where you don't need 2 to the 300 gates, but you need 300 gates, or maybe 1 million gates, a countable number of them. And this is the final piece of good news. It turns out if you need to compute over something that has 2 to the 300 inputs, this is the only way to do it. It really is the only way. Okay, so let me give you the one example that we know very well that quantum computers are good for. And this is really when the field took off in 1995, when Peter Shor, he was also at Bell Labs, he's now at MIT, he showed that a quantum computer can factor numbers into their primes, right? Like 21 is equal to 7 times 3. That's the inverse of multiplication. It's easy for small numbers, but even this number, my laptop can factor this number pretty fast, but I can't do it in my head. I mean, we factor because we memorized usually. So it turns out this is sort of a one-way function. Multiplying is easy, even big numbers. Even numbers with 1,000 digits. We know how to multiply because you could do it by hand. It would take lots of paper, but we could do that. A 1,000-digit number cannot be factored. It's much harder to go backwards. And in fact, factoring, the difficulty of factoring is what most encryption is based on now. It's what when we buy something online, our credit card makes a big number in the public domain, and because people can't factor it, they can't read our credit card number. That's how it works. So if somehow a quantum computer makes factoring easy, that calls into question the safety of all of our encryption standards, and that's absolutely true. Well, this was 30 years ago, and we still don't have quantum computers big enough to be a threat, but the time will come. And so, how does the factoring algorithm work? Well, let's say we want to factor the number 39. Well, yeah.
Why is it important in quantum computing to be able to factor numbers in there?
No, it's just an example. It's one of the only known provable applications of quantum computers right now. It can factor numbers. It doesn't mean it's interesting. In fact, I think in the long term it's not so interesting. And I'll talk a little more about that. But the Shor's algorithm on factoring works like this. So if we want to factor, say, the number 39, how many bits do we need? Well, we need at least 6 bits, because 2 to the 6th is 64. 2 to the 5th is only 32. And if we want to factor 39, we probably need a little more. So 6 bits. And we encode a superposition of the first 39 numbers using gates, a couple of gates. And because it's the number 39, I'm not going to get into this, but Shor showed that we don't need all that many gates to use rule number 1, the wave equation, to go from this wave function. These are just the weights of the wave function, all the coefficients, and it goes from that to that. I'm not showing you exactly how that works, but it does work for any number, and you don't need all that many gates to do it. And then rule number 2, we make a measurement. Yeah, it's random, but we get one of the factors. That's how Shor's algorithm works. It's remarkable because it's a solid application. We can prove it. We know exactly how to build a machine to do this. Unfortunately, this machine is way beyond what we have right now in any laboratory. Now, the bar is getting lower. People are figuring out more efficient ways to implement Shor's algorithm, so it's very exciting. I predict within 10 years, maybe even within 5 years, 2048, RSA 2048, which is the, I didn't put RSA up here, the encryption standard we use now is 2048 bits of information, and numbers that big will be factored in, I think, the 5 to 10 year time frame. Of course, we could just change encryption standards, and then we're fine. But certain government agencies need to know this now. They need to know when encryption will be broken. Because when they keep secrets, they want secrets to be kept for a long time. Not necessarily for banking, but for political timescales, that's long. So it's very important for governments to be on top of this technology, like the when it will happen. But as I said, I think this application, if that's all quantum computing is, it's kind of boring, just a code breaker. Well, it turns out there's another very important class of problem that we don't do very well at computing right now, and these are optimization problems. So this mountainscape here, if I asked you where's the tallest peak, you would immediately say this. I guess maybe it's a little ambiguous, but you'd immediately say this. And the reason is we can plot a two-dimensional topography of this mountain range. There's only 2 variables. There's latitude and longitude, and we have the numbers. We can easily plot it and just look for the highest peak. But what if I gave you a topography with 10,000 dimensions, or a function that has 10,000 variables? A good example would be a stock index, like the Dow Jones stock index. I have a model of what the stock index should be with 10,000 variables that includes the interest rate in Japan, the inflation rate in France, and so forth. The model may be wrong. It doesn't really matter, but we could never even optimize that model because you'd have to test every configuration. 10,000 variables, let's say they only take 100 values each. That's 10,000 to the, no, that's 100 to the 10,000th power. It's ridiculous. Okay, you can't, so Optimization problems we tend not to be very good at. Self-driving cars. Did you know the UPS algorithm for delivery was not to take a left turn? When they make their deliveries, they take only right turns. I mean, it sort of makes sense. It's what we call a heuristic. It's a good guess because left turns are sort of individually painful, but you're going to miss some, clearly it's not going to be super efficient. Anybody heard of the traveling salesman problem? It's sort of like the UPS problem. How do you find the shortest path through a bunch of known places? Well, there are way too many possibilities. And to optimize something like that, we only have approximations. And the reason is there's so many combinations, there's so many possibilities. Only a quantum computer can deal with that much. And so there's hope. Right now, there's no proofs here, and there probably will never be proofs, but quantum computers will likely be able to solve optimization problems like this better than we can using regular computers. To understand the structure of a molecule is also an optimization problem. The electrons on a molecule, they optimize where they want to be to minimize their energy. Two electrons don't want to be on top of each other. They want to be separated. And on a big molecule, I mean, this is not a big molecule. This is caffeine. But it has 100 electrons, and it's very hard. I think nobody can compute the ground state energy, the lowest energy of those electrons in the exact shape. We measure it, and we have approximations. But this molecule is a very important one. It's called the nitrogenase. We know that it fixes nitrogen. It breaks nitrogen into ammonia. N2 is very tightly coupled. It breaks into ammonia, very important in industrial processes, like to make fertilizer, for instance. The only way we make fertilizer and ammonia right now is a high temperature, high pressure process, very energy intensive. We know bacteria can break it down at room temperature and standard pressure. And what seems to be behind that are these funny molecules that have some heavy elements like molybdenum and iron inside these compounds. But we can't model this molecule. We can't even come close. So these are just two examples. There are many where quantum computers really look like they're going to save the day eventually. But mea culpa is that we don't exactly know how that's working, how it'll work right now. Yeah, and when you look at these big companies, they're riding this promise, and they're trying to build machines that will sort of allow us to compute things that you couldn't do otherwise. I mean, these are computer companies. Their future relies on it, I guess. But I will also say that if history is any guide, new generations of technology are usually not invented by the current players at the state of the art. And that's natural. That's fine. So these companies in 50 years, maybe they won't even be here. Who knows what will be here? But I want to talk just a few minutes about a particular type of quantum computer that looks really compelling, but it's so radically different than semiconductors and silicon that these big companies aren't quite playing this game. This is a picture. It's actually from my laboratory at Duke. Each of these blue dots is a single atom. And these single atoms are, it's been blown up so you can see it. This chip, this thing that looks like a bow tie, it's about 1 centimeter across. There's nothing quantum about this chip. It's just a bunch of silicon with electrodes. These atoms are charged atoms. They're called ions. And because they're charged, we can push them around with an electric field. And so the only purpose of this chip is to apply that force field. And this is called an ion trap. The atoms the ions are held, they're suspended above the surface. And the reason you can see them is that they're in a vacuum. I hate to admit that. We're going back to vacuum tubes in a sense. But, well, we have to. We've got to get rid of the air. So there's a small vacuum chamber around this chip. And because of that, when the atoms are there, there's nothing else. So when we shine light on these atoms, and atoms are very discriminating when it comes to light. Most light just goes through. I mean, not like my shirt here. Almost all colors of light will bounce off my shirt. But a single atom only responds at very particular wavelengths of light. We know what they are. These atoms, by the way, are ytterbium. It almost doesn't matter, but they're all exactly the same. They're the same isotope of the same element, and we know what laser to use, and we shine that laser here, and they scatter off these atoms, and we collect that scatter in a camera. It's as simple as that. And so these are the individual atoms. Now, when we turn off the light, the laser light, the atoms are still there. How do we know? Well, I guess we don't know, except that when we turn the light back on, they're still there. So they probably were there when the light was off. Okay? When that light is off, these atoms are rule number one to the extreme. They're totally isolated from the environment. Nobody touches these guys. They're held in space. They're not part of a surface. They're not part of a solid. There's no air. So they're wonderful qubits. In fact, each of these atoms is a pretty good atomic clock. You might know that the best clocks are derived from energy levels in a single atom, the cesium atom actually. And those energy levels are super stable. These are pretty good clocks. They would keep time to a second over probably 1,000 centuries or something like that. So they're pretty good. You can get better ones actually. But that's great for rule number one, where we have isolation, perfect reproducibility of atoms. Now, how do we apply rule number one and apply gates that cause them to entangle? Well, these are ions. If you push them around, they all see it, and that's actually how we entangle them. We use other lasers to do the entanglement. That's basically how it goes. So this is a very compelling architecture for a quantum computer. But I know why Google didn't want to invest in this, because this is a laboratory where the atoms are actually in a little chamber. You can't even see the chamber here. All of the other mess of wires is invested in lasers and optics and fiber optics and optical devices, controllers. We need to tune and stabilize these lasers to about 9 digits of accuracy. It's not hard. I mean, we know how to do it, but it hasn't been, it's not like this has been engineered before. This is a physics experiment. Now, the good news is we've pretty much put everything you saw there in a box, including the vacuum chamber, and we can make gates. And this is sort of a research quantum computer that we had at the university. And you can tell it's a physics lab because we got all the screwdrivers here. But the box, the vacuum is not in the box. The vacuum chamber is pretty small. But there's all kinds of optical devices that we can tune from outside the box. And putting the box is important because there's air currents that destroy things. And we want to get rid of that. We want good temperature control. All this control of the environment that's so important to maintain rule number one. Now, when we want to apply rule number two, we can just look at the atoms like this picture here. We flash on a laser and we see which ones are 1 and which ones are 0. That's fine. So it's very rare in science that we have, in the natural world, that we have a system that we can apply rule number one when we want to, and we can apply rule number two when we want to, and we can switch back and forth without crosstalk. And this is probably the best medium to do that. And so, lo and behold, we formed a company. I didn't really want to form a company, but some venture capitalists approached us and said, you know, your stuff looks like a business plan. We think you should form a company. And after several years of back and forth involving the universities, we formed the company IonQ. And again, things just went really fast. That was in 2016, and in just 5 years, they went public, actually, due to just great investor exuberance in this field as a whole. I think the AI craze we're going through right now only helps. I didn't mention AI, but that's one of the problems we know now, when the limitations of large language models is that they can only make about 1 trillion calls to a computer on these data centers. We would like it to be 1 billion trillion, but there's no way to do that without 1 billion data centers, and we're not going to have 1 billion data centers. Quantum allows us to maybe perform these optimizations that are needed in large language models. It's very researchy. We don't know exactly how that's going to play out. In a sense, you have to build these machines and sort of see what happens there. And by having a company, at least we can start the process of engineering something like this. I want to go to that picture. To engineer this, put it in a package, sell it, get users to play around. That's really the business plan for IonQ, is to get customers to play around with these. They're still small quantum computers, but learn how to program them And as we scale, we're going to make them bigger. Hopefully something will pay for that because it's not going to be cheap. But if we find an application that hits some sector of industry, people will be willing to invest in doing this engineering. Again, we've had 75 years of VLSI, very large scale integration of silicon. And that's why we have the amazing machines that we have today. We haven't even started doing that in quantum. There are different technologies. These ion traps I mentioned are probably in the lead, but there are a few others that are of interest. And by the way, none of these, I showed the picture of the CEOs. This is a little bit of a joke. Amazon had a chip. I added that as a joke, me too. It's like they don't know what they're doing. I don't even know what that chip is, but they have a quantum chip. They have no idea what they're doing. But I'm glad they're in the game because they're hiring students that I train. They get PhDs in physics and go work at Amazon. That's great. But it's probably not going to look like the silicon chip on your laptop. It's going to look exotic. Look, quantum computing is an exotic way of computing. It demands exotic hardware. Okay, so back to back to sort of business slides. Many of you might know what this curve is. It's called the hype cycle of a new technology. Expectations over time, and when we have something new, like AI, like the automobile, like digital cameras, for instance, or flash memory. There's clearly a long-run expectation that we're going to deliver great products and so forth. But we get over our skis a little bit, and it gets overhyped, and people start to lose interest because we know it's going to take a long time to get there. And unfortunately, many of these business cycles, I'm not claiming that quantum is destined to follow this, but there's a lot of hype in the field, and we don't yet have the production. And what we worry about is that people will get disillusioned. It's like fusion energy. I mean, we know the physics is good, but people are sort of disillusioned. It's expensive, and it's always 50 years away or 20 years away. And if expectations get low, then nobody will invest in it, and it'll never happen. So you have to sometimes forge through that, power through that somehow. And time usually helps. We learn more. We get better at the engineering. And there's finally a plateau of commercial utility at the end. And quantum could fall prey to this path. However, I will say that today's quantum computers, even the ones in my lab at Duke and the ones that IonQ makes and even the ones IBM and some of the other companies make, they're being used right now for science. These are not paying the bills necessarily, but I'll give you an example. We use a very small quantum computer with about 12 qubits to do a very simple model of a simple process that's thought to occur on the surface of a black hole in cosmology. You may have heard that the information on a black hole is actually not in the volume of the black hole, it's only on the surface. And it turns out there's a process that goes on, it's specifically in a black hole, that we were able to model with this 12-qubit quantum computer. Now, no company is going to buy that service, but when you can do science at that level, cosmology, things like this, high-energy physics, simulating nuclear physics, that's happening right now, even with small systems. And I do believe that scientific use of quantum computers can really help avoid this trough. The industry, they're going to watch the science happening, and they're going to stay interested. People will stay invested. I see signs of that happening. So it's actually very important that universities and governments keep the pedal to the metal on this one and invest in it. And in fact, this slide it's dated. It's a couple of years old, but it gives roughly the investments. I don't even know over what period. I'm thinking it's probably 5 years from like 2018 to 2023. The countries in the world that are investing in quantum. U.S. is just the government has put in many billions. Look at China, 25 billion. And I'm not sure where that figure comes from, but they're putting in a lot more government money than we are in the U.S. However, in the U.S., industry is now putting in a lot more money than government. And our industry in the U.S. is the envy of the world, definitely is, even China. So it's very interesting what's going on now. This is fundamental science, but industry is sort of the backbone for it. And I've been back and forth, academic and industry. I sort of see both sides, and I worry a little bit that neither university nor industry kind of has figured it out exactly. They're both very important, but at the university, we're okay with rule number 1 and rule number 2. We're quantum physics departments. We have no problem talking about the philosophical implications and so forth. We're very comfortable with the rules of quantum physics, but we don't engineer things. Universities are not built to build helicopters that you will fly. Okay? That's the focus of industry. But industry, again, it's getting better, but we need real engineers to learn these rules so that they can build things that can be used as quantum technologies. I think also industry, the big industry anyway, they favor conventional computers. If it's another computer, it's probably going to look like this one that worked for 50 years. But we went from the horses to cars. It was a big sea change. And so it probably won't happen from conventional industry. But that's where the engineering has to happen. And I do think there's maybe a period of time, a few decades, where there's something in the middle. Government laboratories might be good targets, but maybe even something else. Maybe not all that involved with government. Maybe some industrial leaders would form an institute of some sort, and it's not a university either. So they can do engineering and hire staff engineers and so forth. So, yes, question.
I'm not exactly sure how it's going to come out. But you were saying that you needed good engineers, and I'm a retired school teacher. And I would think that courses need to be taught as early as elementary school to get for students to be prepared to learn and to learn this. And what I have seen is that perhaps some schools would be able to produce those types of engineers. But there are many schools who, let alone do quantum. If you recall during COVID, there were children who could not even get on the internet and had to go to McDonald's in order to use computers. And this is at such a high level. Who is going to do this?
Well, oh, by the way, this is my last slide, so let's transition over to questions. That's very good. So, so to your question, if you didn't hear, it had to do with what can we do, even K through 12, or early education, to somehow help promote the vision I gave you. Now, I think the rules of quantum can indeed be taught very early. You don't need, the one thing you should walk away with at your cocktail parties, you don't need the math. I mean, to be a professional, you have to you have to get there with the math. But the concepts, they're so amazing and weird that I find that people that learn them for the first time are amazed. I was super frustrated in college when I learned these rules. It didn't make any sense. But your second point, that how do we get good engineers out of schools? Well, engineering is a very funny discipline. I'm not convinced that you learn in engineering even in college. You can get a major in engineering, but what are you doing? You're learning chemistry and physics, basically, maybe more applied. But real engineering is about reliability, manufacturability. These are things that it's very hard to teach. Here I am, an engineering professor. So I think what we can do is teach physics or even quantum physics at an earlier age. There's so much resistance to that, to bringing it early. Usually, if the only physics kids take is in the senior year, they're in 12th grade. There was a movement early on to bring that to 9th grade and then get more complicated in terms of complexity of matter. Physics, chemistry, and then biology. But it's actually the other way around. We start with biology partly because it doesn't require as much mathematics, but it's very high level. Biology is very compartmentalized. There's a lot of information there. And then chemistry, and then physics because it has all the math. The thing is, quantum doesn't have all that much math. It doesn't have to be taught that way. So I appreciate your question. Yeah.
You said on your slide that the U.S. government is only spending about $2.5 billion. Is that correct?
Maybe $1 billion a year, something like that.
Well, compared to, let's say, the Chinese, if you added private industry, what they are spending on quantum, how would that number of 1 billion change?
Probably about factor 10. I think it's 10 to 1. It's 5 or 10 to 1. I don't know. The number's big. Industry to government. And in fact, the U.S. government is kind of worried about that. They want to have their eyes on this technology because it's so important for national security, actually. So it's an interesting conundrum. All the other countries are almost entirely funded by government only. So the U.S. is safely in the lead by a wide margin. You won't hear that. You won't read that in the newspaper. And when I go down to the Hill, I was just there last week lobbying for the new National Quantum Initiative. It's not what you say. You say, "Oh, we're fine. We don't worry about the Chinese." Congress likes to hear us say that. "Oh yeah, we have to worry about the Chinese," and they're doing very good research in China, way better than they were 20 or 30 years ago. And they are very focused. Now, the thing that China has that we don't is their industry, their academic, their universities, and their government. They're all the same thing when they want to be. They're really intertwined. Whereas the American way is independence. We have all these silos. So it's a different system, and I think we're set up to win this one. But it's interesting points you make. Yes, in the back, and then you. Two. You and behind you.
So there are quantum computers that are being used right now. What is there programming languages? Are you writing in assembly? Are you writing in?
Yeah. I wish we're lower level than that. We're not even at assembler language. We're coding in logic gates, ands and ors. Yeah. It's really low level. Yeah, it's like a quantum version of an AND gate. Oh, I'll give you a good example. You know what a NOT gate is? A bit. What can you do to a bit in the non-quantum world? You can leave it alone, or you can flip it. That's called a NOT gate. In quantum, we can have something called the square root of NOT, which makes no sense classically. What is the square root of NOT? That's the operation which, when applied twice, is a NOT gate. Now, I just told you what you can do on a regular computer. There's only two things. You can either do nothing, or you can flip the bit. If you do that twice, you end up where you are, both cases. So if you do anything classically twice to a single bit, you end up where you started. But I just said a square root of NOT gate is something when you do it twice, it flips the bit. Well, obviously we're making a superposition. We can sort of flip it halfway. So 0 becomes a superposition of 0 and 1, and then the next application, it completes so that's an example of a superposition, and when you do it with multiple qubits, like a square root of AND, then you can make entangled states and so forth. So that's the interference. And I hate to say it, I'm embarrassed to say it, that's how we program. A quantum computer program actually looks like a logic gate tree. It's horrible. We don't yet have the higher level, even the assembler code. It's really primitive. However, we have all this power. We have the 2 to the 300 sitting there. Yeah.
Before we get into the next question, I know we have a little bit of a transition we need to do. Brad?
Oh, sorry, I jumped the gun for you. That's it.
All right. So thank you, Chris, for clearing this up. I think we can definitely say we all now have at least a better understanding, or maybe even more questions than whenever we arrived here tonight. But we're going to go ahead and go into the formal Q&A section here. And if you could raise your hand, we will bring a microphone to you because that will help our friends who are watching this online also hear your questions. And it'll help to make sure that Chris gets a chance to hear those questions nice and clearly. So do raise those hands up. And if you're watching us on the YouTube stream, go ahead and type that question into the chat, and we will ask those on your behalf here.
I think we've got someone
we'll
over
go ahead
here.
and get started.
So when you look at stories, you see like about 2 years ago, I think there was a story, Google's quantum computer has solved a puzzle or a problem that would have normally taken 100 or 200 years.
A pentillion years,
Or
I think.
whatever it was. How do we know that they got it right?
You almost answered your own question. We don't. Yeah, many of these exclamations of a breakthrough, when you look at them, it's interesting physics, but it's sort of akin to producing random numbers. Oh, they produce these random numbers. It's like, how can you tell?
I think we have a question online.
We have 2 questions online, work from our online audience. The first question, with quantum, how does one encode an algorithm or observe a result?
Okay, the first question, how does one encode an algorithm? Now, I gave an example of the factoring algorithm, factoring the number 39. There was an earlier question before the Q&A session kicked off. Do we have a programming language? The answer is no. But we know what pattern of logic gates are needed to do the computation. Think of a simple adder. You might not know this, but if you have numbers represented by bits, zeros and ones, there is a well-defined sequence of operations using the NOT operator and the NAND operator, whatever your CPU typically uses. And there's a very well-prescribed way to add 2 numbers together. And even if you have to carry, if there's a carry bit, you have room for that. And that's similar to what we do now with quantum computers. We express the application in terms of a sequence of logical operators. And it's not like reading a Python code. There are no English words. So it's very difficult to look at a graph of gates and say, I know what that's doing. No. But there are lots of ways to look at it, and I didn't even mention that we don't need to use just bits. We could use different types of quantum systems. It's sort of like the can is open. There's every possible quantum thing could be used as a computer, and you have to program with it. The great thing about silicon and bits is that when you put 2 transistors together, you get a NAND gate, and we just said, okay, we're going to build NAND gates. That's all we're going to do. And we did that for 50 years. And it gave us these computers. We don't have that standard yet. Not even the hardware is standardized. Atoms, superconducting loops of wire, individual silicon spins, photons. We don't even have the hardware lined up, much less a programming language or even a standard set of gates. So yeah, work in progress.
Following that, our second question online kind of trails off this next one. What do you think is the timeline for quantum computing to develop to the point of programming languages of some type, where the underlying physics works reliably enough that we can build interfaces above it?
Yeah, good question. When will we see a programming language? Another software question. I think it's sufficient to get to a use case of quantum computers using just gates, because what's hidden behind the quantum computer is this exponential growth of state space when you add quantum bits together. So we're willing to live with the primitive gate language. And if we can find some near-term niche application that creates commercial value, it needs to be commercial value because we need investors to engineer better systems and make the software. That's when we'll start to see software, because it will be an application that has been, it's been standardized, and that's usually the case you need to make before you write software. You write software only because people are going to use it. And so if people are going to use a quantum computer in a certain direction, you should write a software to do all the shortcuts of certain gate structures for that application. Remember I said it's not obvious looking at the gate structure what the application is. But if we can, and we can't write software to decode any gate program. But if there's a particular gate program that's useful, there will be software. It will follow right away. It'll be easy. It'll come there, and then people will be able to run that particular niche. And then we go to another application. Hopefully, it'll be kind of snowball going downhill, as they say. So good question.
Other questions? One over here.
So in modern computing today, one of the largest challenges is circled around the ability to bring in enough power in a series of chain systems in order to deliver the amount of computing power in a data center, right? I work in data center software, and one of the things that we deal with a lot is the limitations, like on a per rack level, on a per data center hall level, of the amount of power that you can bring in, but also the fact that that creates a lot of thermal energy when you're using that in computing on the actual silicon chips. In understanding that limitation from a thermal level, is there some application that quantum computing could bring in that would not only greatly increase the amount of computing you could do with a qubit versus a bit, but also impact the amount of computing we could do in a large chain like at the size of a data center?
Okay, a couple questions there. I think the energy it takes to compute, that actually scales very nicely in quantum computers. Because again, all we have to do is add one atom to double the strength of that computer. So energy is really not the bottleneck there. But I think you brought up maybe a more interesting question. Can quantum computers be put to use to more energy efficiently do regular computing? And here's where, I don't know where to stop. There's so many kind of applications from optimized nuclear energy. I mean, one problem in fusion is that the turbulence of the plasma in certain types of fusion reactors, we can't model that turbulence. It's like the weather problem, computing the weather. And quantum computers might be able to edge us closer to understanding how to model turbulence. That's just one kind of fringe example. Another one is network problems. I mean, a data center is a large network. It's modular, and there may be more optimal ways to deploy different nodes of a data center, and maybe a quantum computer would help you understand the decision tree on how you break up the computer. I'm not an expert in that field, but again, the second application space I gave was optimization. That touches everything. And I think, and people talk about power grids. I don't know much about the electricity grid in the US, but it's a bunch of disconnected modules. It's not very efficient. I know there's a lot of energy loss just connecting those power grids together. Yeah, I could go on forever probably, but it's an interesting question. And it's one of those niche fields that people, even at power companies and certainly the big computing companies, are thinking about quantum computers for their problem.
Other questions down here? All right, one moment.
Oh, hi. Yeah, I just had a quick question. So I've heard about the difficulties in designing of hardware for quantum computers, particularly error correction. What do you think is the real thing holding back the quantum computing, I guess, industry, if you could call it that yet? Is it the hardware or the theory, knowing what to build and how to build it? So would you rather see breakthroughs in the theory of quantum or, actual chip design, or, if they're too intertangled to even de-aggregate at this point?
Okay, the question concerns what are the bottlenecks in building hardware? I would actually break the hardware into two classes of hardware that's being pursued right now. And I sort of hinted at these different flavors. One of them I would call synthetic qubits, and that is building qubits out of chunks of matter. I didn't talk about it much, but what IBM and Google and so forth are doing they're using little superconducting currents. And now, if you know what superconductors are, it's a marvelous physics effect in its own right. It involves electricity flowing without loss. Okay, that should wake you up, because in quantum, if electrons flow without loss, that means they're kind of unobserved. They're not bumping into things. So it turns out that's a perfectly good qubit, a loop of wire in a certain way that's kept very cold, so it's superconducting. Now the problem is when you build another qubit, it's not going to have the same dimensions. It's going to be a little bit different. if you build 1,000 of these qubits, they're all a little bit different in certain ways, and those differences can even drift in time. So it's sort of a mess. And so I think on the synthetic qubit side, the scaling is hampered by the fact that we don't know how to quickly calibrate all those differences. We don't know how to cool such a big system. We have to get them nearly to absolute zero temperature, and that takes a lot of energy. I think that's sort of an engineering problem, but it's not clear how to get to 1 million superconducting qubits at all. Nobody really knows that. Okay, the other class of hardware is the one I talked about briefly, these atoms, or electrons, or photons, or atomic ions. These are so-called natural qubits. These qubits naturally exist in nature. We don't fabricate atoms. We have to, I didn't tell you how we put the atoms there, but you could imagine atoms of, say, chromium. You get a piece of chrome, and you evaporate some off, you'll have individual atoms. You don't make the atom. You get it there. And so all the atoms, you can make sure they're exactly the same element, the same isotope. And so the manufacturing process is not the bottleneck there. The bottleneck is the engineering of the controllers, because there are lasers, there are optics, there's microwave fields, vacuum chambers, things that, as a society, there's very little experience in manufacturing stuff that has all that. So the bottlenecks depend on the sector. And it's funny that they're kind of complementary. I would tend to, of course, I'm not unbiased, but what I like about the natural quantum systems is that challenges of engineering will be met. They're not physics. They're not challenges of physics. I think some of the solid-state qubit technologies, like superconductors, those are real physics problems. When you make a qubit out of 10 to the 18 atoms, if you ever looked at a micrograph of a chip, it sort of looks like a shag carpet. It's noisy, and that noise. There's some physics there that I think we need maybe breakthroughs in materials for that to work. So yes, my answer is all over the place, but different companies have different challenges. I rolled my eyes there just because the brain is room temperature. It's sticky and wet. I mean, that's not a good place for rule number one to work by itself. That said, I'm not sure the brain can understand itself somehow. That bothers me, that the brain could understand itself. We seem to understand the rules of quantum mechanics, but the brain, I think, is higher level. Somebody tried to corner me into consciousness earlier, but I avoided that one. But yeah, so many people subscribe to this, though, and there's some compelling things that go on, like in the eye, at the single photon level, that seem to have quantum things going. Anyway.
All right, other questions? Okay, there's one over there.
Can you just explain, for a qubit, how many states can it have? Like, bits have 2. I like that. What about qubits and the gates? Like, how many different states are there?
So a qubit, by definition, is only 2 states, because it's qubit. So the language is, there's qtrit, I guess, for 3, tertiary, and then we go to qdits, D. I'm not sure why D. Anyway, so the variable number. Those are different ways to store information, and it's sort of natural. Atoms, not individual electrons so much, but even superconductors, they have more than 2 levels. So why don't we take advantage of packing more information? And we can do that. The price we pay is that the gates that we need to move that information around aren't as advanced. And it's partly because of our experience in classical computers. We work with bits. We have the AND gate, we have the OR gate, and that's good enough. We know it's sufficient. And so to start in quantum, we build a system that's sufficient. Qubits, 2 levels. They're sufficient. If you only had 1 level, it would be boring. There's no information there. So you have to have 2. But your question is a good one. A lot of people, it's still early enough in the game that people are looking at tertiary systems. There's one of my colleagues up in Waterloo, Canada, has a 24-level quantum system. And she's able to, I'm not sure she can do gates, but she can measure every one of those 24 levels with near perfect efficiency. It's an atom that has lots of levels, that's all. Not sure how useful that will be. Maybe there will be some niche cases where that's used. Depends on the app. Maybe if somebody comes along with an application and says, you know, if we only had a 7-level system, that would make things a lot easier to program here. If that comes up, then we'll make 7-level systems.
I think we have a couple of online questions.
We had some questions involving a few things here, but I want to just paraphrase this one for a moment. It says they were asking about companies that are selling access to quantum computers, as well as they're asking about you can go online now and buy quantum computers, like 2,000 qubit quantum computers. So can you comment about some of these companies and some of their technologies that they're giving access to this to the public?
Yeah, many companies are giving access to computers, and I even showed a slide. My company's doing that too. In fact, I didn't mention it, but for about a year in 2018, I was the CEO of IonQ. There was only 30 people. We were a small startup. I sort of accidentally fell into that role. But one of the existential decisions while I was CEO was we were building our first prototypes. And the question was, do we put our system on the Amazon AWS cloud for people to get access to our system? It was a very small quantum computer. It only had, I think, I don't know, 10 to 20 qubits or something. It was a machine that would not be able to solve anything you couldn't solve on your laptop, but it would allow people to practice computing and do gate structures and maybe recognize, study the interference, factor the number 15, little tasks like that. And I didn't want to put the system on the cloud, and the reason was we were a company of 30 people, and I didn't want engineers sort of wasting their time making sure a system was up 24/7 all the time, and we could do maintenance, and we had to make sure, because that meant we were not making new and more powerful systems that were required. And I was convinced otherwise, and I'm glad I was. I was wrong. It was really important to do that, to put our system on the cloud back in 2019. And the reason is, when we made it run 24/7, we learned about the bottlenecks of our engineering. We learned what it takes to make something reliable. We learned so much that I'm not a classically trained engineer. Many engineers may have seen that as obvious. But okay, so we and others, IBM sort of started this in 2016 or so. Their systems have been online ever since then. They have lots of different machines. You mentioned, the questioner said, what about buying a machine or one with 2,000 qubits? Nobody has a system that fully uses 2,000 qubits. And if they do, they're probably being less than truthful. There are companies that go out there and say, here's our 2,000. It's easy to have 10 million qubits. I can give you a chunk of material that has 10 million atoms in it. There, 10 million qubits. You need control of them. You need to operate rule number 1 and 2 exclusively on all of the qubits. And these companies that advertise they can do it with 2,000 qubits are not telling the truth.
And one more question from online. This person is kind of follow up to something you were talking about earlier, so the timing may be a little off, but superposition is claimed to contain all of the solutions. How do you then select or observe the right solution?
Oh, that's very hard to, there's no way to answer that easily. The closest I can come, I'll go back to the factoring algorithm, if you remember this slide here. These red dots, these gates, they're supposed to denote, it's very hard to draw this, but they're supposed to denote interference between colliding paths, whatever that means. Time is loosely going from left to right here. And the pattern of exactly where in time and place these red dots are placed, that is the circuit. And encoded in where they are is the thing you're trying to solve. Like when I factor the number 39, somehow the number 39 is uniquely represented by the position of these orange dots. And this is the magic of the algorithm and so forth. Every algorithm has its own pattern and so forth. But when you program a quantum computer, you have some information you're looking for. Maybe you're trying to maximize a function, and the function itself is stored in where these gates are. I've said that several times, I guess, tonight, but I hope I it's tricky. It's better if you have a concrete example of an algorithm, and then I can just show you what the gates look like. Done.
I think we have time for just a couple more questions. Does anyone have any other questions? Our brains are very full.
Everybody ready for your cocktail party?
Well, if that's the case, how about a round of applause for our amazing presenter?
Thank you.
I'm just sad that they didn't mention the quantum realm once. Not once. That was my joke for my comic book friends. Well, folks, my name's Jill, and I'm here to say goodbye. But I would like to encourage everyone to please check around your seats, make sure you didn't leave anything behind. If it's good, we're going to keep it. If it's bad, it'll be in the lost and found. If anyone has any further questions, as you make your way out, I don't know if our presenter has any more time, but thank you so much for being here. We always appreciate seeing so many wonderful faces at our cafe side. Thank you very much.